Hi, this is Miss Barber. This section is 3.7 Optimization. Let's work out a few examples. Example: an open lid box is to be made by cutting congruent squares from the corners of a 12 by 12 inch sheet of tin and then folding up the flaps. How can this be done to maximize the volume? Let's begin this by drawing a representation for the 12 by 12 inch sheet of tin. Should look like a square. We know that each side is 12 inches in length. Now the instructions say we're going to cut out a corner from each of the four, and they're going to be of some length. That's what we're solving for, so they'll all be length X. That tells us that when folded up, the length between the two cut corners will be 12 minus the two x's. So to begin with, since we want to maximize the volume, remember our objective is to maximize the volume. Let's write out the formula for the volume. The volume is the product of the length times the width times the height. To be able to better see this, let's attempt to sketch the box in 3 dimensions. So we would have a side. Pretend like they're the same length. The length of what looks longer, those would be 12 minus 2x on all 4 sides of the base because the base is a square. And the height would be the x. Replacing those words of length, width, and height with a formula, we would have that the volume with respect to x is equal to, let's say the length is 12 minus 2x, the width is 12 minus 2x, and the height is x. Multiply these 3 terms together and you get the cubic polynomial 4x cubed minus 48x squared plus 144x. Before we proceed, we need to determine the domain, and while the formula for the volume is a polynomial, so we're not concerned with respect to function behavior, we are concerned that we are working with a volume, so we have physical constraints. The height has to at least be 0, and the measurement of the length and width has to at least be 0. So we'll solve the 12 minus 2x is equal to or greater than 0. And when we finish solving, we get that 6 is equal to or greater than 0. Combining the fact that x must be equal to or greater than 0 and x is equal to or less than 6, the domain of the volume will be between 0 and 6. Now we're ready to solve for the extrema. That is, we want the local min, local max, we want the max. To get the extrema, we always start by finding critical values. And critical values are where the derivative equals 0 or the derivative does not exist. Either way, we have to find the derivative first. So let's take the derivative of the function we just obtained. We get v prime of x is equal to, bringing the 3 down and multiplying it to the 4, that'll be 12x to the 3 minus 1, that's squared. Bring the 2 down and multiply it to the negative 48. The product is negative 96x, and the derivative of 144x is just 144. Let's go ahead and factor this. Oh, but before we do, notice that the derivative is a polynomial, so we know that there will be no place for which the derivative does not exist, so we only need to solve for where the derivative equals 0. Let's factor here. If I factor out a 12, I get x squared minus 8x plus 12. And we'll factor the quadratic. That gives me, let's see, 12 times x minus the factors of 12, whose sum or difference will give me 8, is 6 and 2. So x minus 6, x minus 2. Let's set that factored form equal to 0. We want to solve 0 equals 12 times x minus 6 times x minus 2. Solving, we'll get that the critical values are x equals 2 and x equals 6. We have to determine which, if either of those, will give us the maximum volume. Got to check that. To do so, I'm going to use the second derivative test. To use the second derivative test, we need the second derivative, so let's compute that. V double prime of x is equal to, we're going to take the derivative of the derivative function. Derivative of 12x squared, bring the 2 down and multiply it to the 12, that makes it 24x, minus the derivative of 96x, that's just minus 96, and the derivative of 144, which is a constant, is just 0. Let's evaluate it in each of the critical values. So I want to know the SIGN of the second derivative evaluated at 2. That's 24 times 2 minus 96. You don't even have to compute that to know that's going to be less than 0. Less than 0 means it's negative. And for second derivative, if it's negative, then it's a concave down, and we notice at the most extreme point gives us a maximum. So we know that when x equals 2, we get a max. Let's see what happens with x equals 6. The second derivative evaluated at 6 is 24 times 6 minus 96. And again, you don't have to compute this to know that that difference is a positive number. And if the second derivative is positive, it tells us that the shape is concave up. And if it's concave up, the most extreme point is a minimum. Let's remember what the domain was. The domain is 0 to 6. And we see that if you compute at 0, you get a volume of 0. And if you compute at 6, the length and the width both go to 0, which will also give you a 0 volume. And that would be the minimum volume you can have. We want the max. We write to maximize volume, cut out squares of length 2 inches from the 4 corners.